Count the number of vertices, edges, and faces of what is left of a pentagonal prism, a prism whose bases are pentagons, after three small original vertices are cut off. So what we're being asked to do is find the number of vertices, edges, and faces of a prism with a pentagonal base after we cut off three of the original vertices or corners. Now, ideally, you should be able to do it without a picture. That's our goal. But when I solve the problem, I will use a picture just to explain a few things. But your goal is to do it without any picture. Your goal is to visualize the solid so that you can solve the problem. I have the question on top, the exact same question here. I'm going to refer to it. And I know I have a prism here, a prism with a pentagonal base. I can visualize it, but I'm going to use it here to explain the solution to the problem. And I know I'm supposed to cut off three small corners. I just cut off one corner. Okay, so let's try to fill out this table very carefully. What is the total number of faces, vertices, and edges of the original prism? Well, the total number of faces would be 7 because it has 5 lateral faces and 2 bases. 5 plus 2 is 7. The total number of vertices would be 5 on the top base and 5 in the bottom base, so it's going to be 5 times 2 or 10. And the total number of edges would be 5 on the top base, 5 in the bottom base, and 5 around. That's 5 lateral edges. That's going to be 15. And this is something you should be able to do without a solid. I have a solid here so that I can explain to you where the numbers are coming from. Now, let's analyze what happens when we chop off one vertex. What happens to the total number of faces? What happens to the total number of edges? What happens to the total number of vertices? Now, when you chop off a corner, you increase a face. The total number of faces goes up by 1. But we are chopping off 3 corners. It doesn't matter where we chop off. It could be here, it could be here, it could be here. I would gain 3 faces. So the total number of faces would be 7 plus 3 or 10. Now, when you chop off a corner, you lose that corner, you gain 3 corners, so you have a net gain of 2 corners for each cut. Each time you cut a vertex, you lose that vertex, but you gain 3. That means you have a net gain of 2 vertices per cut. This you have to pause the video and genuinely understand what I'm saying. 2 vertices per cut. And there are 3 cuts, so we will gain altogether 3 times 2 or 6 vertices. 10 plus 6 is 16. Okay. What happens when we chop off a corner? What happens to the total number of edges? We increase the total number of edges by 3 for each cut. Each time I cut off a corner, I add 3 edges. So if I'm supposed to cut off 3 corners, I'm going to be adding 3 times 3, 9 edges. 15 plus 9 is 24, so that'll be the total number of edges. So my answers are 10 is the total number of faces, 16 is the total number of vertices, and 24 is the total number of edges.